If I grew that much in 2 years, that's clearly a problem.
Did it work?
There must be some.
Yeah. I can put your phone in charge.
Yeah. You needed a no postdoc to come back.
Yeah, we just pushed some new bosons. There is a new boson.
So now it's one.
That's
Yeah,
only push that.
can you hear me now?
Yeah, they can.
Oh, okay.
Yes,
Good.
we can.
Yes. Right, so what I was saying is, do it again. Like if you have spinning black holes, and we know we have because LIGO have observed black holes merge to produce spinning black holes. And if we have a hypothetical particle, which is called a photon, and that's the only ingredients that we need, then through the black hole superradiance process, we'll populate superradiance cloud, a vector superradiance cloud around the black hole, and the resulting strong field electromagnetism will lead to the population of dark particles in the cloud, which leads to a very bright X-ray source, which we will call a new pulsar. So we'll see how each of these steps work. And I will, but let me first start with a short introduction to the black hole superradiance process. Okay, so the black hole superradiance, the superradiance process was first discovered by Zanovich, and in considering like a rotating cylinder. So if you have a rotating cylinder with a surface that has friction, and then you are throwing a little, let's say, a ping pong ball onto the surface, then if the cylinder is rotating very fast, faster than the speed of the little ball, then the little ball will hit the cylinder and get accelerated through frictional force. While if the cylinder is rotating very slowly, then the ball will lose energy and slower. So here, like there's an important concept, which is the superradiance condition. Basically, if the rotation frequency of this rotating object is faster than the angular frequency, angular velocity of the little sphere, then the little sphere will extract energy from the system. Okay, so there is a direct black hole analog, which is known as the black hole superradiance process, where now if I send a wave onto a rotating black hole, then if the angular velocity of the black hole is larger than the angular speed of this wave, then this wave will bounce off the black hole and get amplified. So in this simulation, hopefully it shows, what you are seeing is if you scatter a black hole onto the black hole gravitational wave, after the scattering, like it will come out amplified. So around 2010, Mina and Sergey pointed out that now instead of having a relativistic wave or a massless wave, like a gravitational wave, if we have a massive particle wave made out of light bosons like exponentially and photon, then this wave will scatter with the black hole, but due to the presence of the gravitational potential, it will get bound. And as a result, we'll just keep bouncing off the black hole until it gets almost all of the angular velocity of the black hole to the point where the superradiance condition is no longer satisfied. Okay, so in this way, what you can get is to populate the region around the black hole with really high amplitude bosonic wave of massive particles. So since we are talking about one state, we need to switch our description of the system to studying like the wave function of this one state instead of something that we're scattering with it. So here the process is mostly determined by the gravitational potential, like the Newtonian potential, where the parameter combination of G Newton times the mass of black hole and times the mass of particle. So the photon mass is on U here, so on the top. This combination is analogous to the fine structure constant in electromagnetism. So and you should treat this potential as basically like the electric static potential around a photon and study the electron wave function around it. Here you are treating the gravitational potential as a potential that is bounding this boson, which is populating some energy levels around it. So here, this combination, which we'll call the gravitational fine structure constant alpha, will take value between, let's say, 0.12 to 0.1 or even 0.4 throughout the top. So, and it also represents the physical meaning of it. It also represents the ratio between the horizon size, GM, of the black hole over the Compton wavelength of the particle, right? So if the particle has a wavelength that is slightly bigger than the horizon size of the black hole, that's when like the effect we'll be talking about is the most interesting.
All right. Do I need to source those massive bosons from as they are dark matter or from other
No,
sources?
like you don't. Like you can start with like some quantum fluctuation in one particle, and the process will drive instability, as I will show you now.
How do we understand the value of alpha that you choose?
Oh, so like for why am I keep going forward? Oh, okay, yeah. So the value of alpha, like we're choosing is basically like choosing the mass of the photon, right? Like if you make it a little bit heavier, then like the alpha photon will be bigger for the same black hole mass. So here, so at the top, we'll mostly be talking about solar mass black holes. So this combination is roughly like a kilometer. So we'll be looking at dark photons with mass that is order 10 to minus 11 eV or somewhere around that, where the wavelength of the particle is comparable to black hole wavelength. Okay. So yes. So now my computer. Okay, so now I lost. So what you seeing here is basically the superradiance instability at work. So even if you start with basically zero particle around the black hole, through some fluctuation you get a 1, and due to this exponential instability, this number of particles around the black hole will grow exponentially until it extracts almost all the angular momentum from the black hole. And as you can see, the profile of this vector field around the black hole is somewhat regular. So this motivates us to understand what is wave function of this cloud of particles. So the wave function.
Sorry, how would the interaction between those bosonic particles change the picture?
So here, like we are talking about like a U1, right? Which is not
but there are many other. There can be other particles around black hole that can interact with this.
So I'm going to show you.
Yeah.
When it interacts with others. Yes. So here, like just the U1, and I'm just introducing it to you, like how this process.
When you show these videos, what does the color mean?
Oh, so the color just means like the strength of the fields of the like all the like energy density at a single location, where it is mostly like near the black hole that is the largest. All right, so so this is the wave function you are seeing, where I'm plotting the A vector field, which is the dominant component. And the mode for vectors, the mode that is the fastest superradiating is this mode which has L equal to 0, J equal to 1 because S equal to 1. We are talking about vector field, and M equal to 1. So this mode is an S wave state, which is rotating around the spin direction of the black hole, which points in the B direction. So at any time, the A vector field is always parallel to each other, pointing at a particular direction. And then, like as time goes on, like you are rotating along the spin direction. So like me, like and the spin direction. So this is the structure. Yeah.
So in the scalar case, like I feel like I've heard the argument that you don't need to worry about like GR effects because in the scalar case, the P wave is the dominant one, like there is no S wave. So everything's sort of far away from the black hole.
Right.
But here in this case, if the S wave is dominant, don't you actually have a lot of the wave function near the center?
Yeah, so there are GR effects which are important when alpha is large. And there are numerical studies by Will East which works out all these details. For my talk, throughout the talk, like this is something.
Okay.
Yes, so
Is there, sorry, is there a hyperfine structure like this cloud has an angular momentum and the like a nucleus, like a black hole has an angular momentum. So one could have a interaction between the two and the hyperfine structure. Is that correct?
I think these corrections are taken into account when you compute like the wave functions, like numerically. Analytically, I'm not so sure because I think like these effects are smaller because the
hyperfine is a small effect. I'm just asking if that whether this leads to a level splitting.
Oh, like so it might, but like the important thing is like this is the level that is not only like the fastest superradiating, it is the level that is also like if it were to be decay, it will be also the one that has the largest like a decay and like a decay rate.
It's also very specifically oriented.
Yeah. So this one like has the largest imaginary part, And as a result, like if you mix with some other state which might be decaying, like it. But like now, like if you introduce some additional like a black hole, right, which put it in a binary, then like this affects other. All right.
So if I view there's vector field and there's a black hole which is rotating, there are stable configurations for the system, maybe a higher excited state, right? Here we're talking about the ground state.
Static.
Yeah, stable, but there's a particular angular momentum configuration for the system. Are there stable solutions?
What do you mean by stable?
Static.
Yeah,
Static?
more static.
Time independent? No, like there are no time independent. Yeah. Because like mostly because like the K is always smaller than M. So like omega is always negative.
Well, if I give this vector field extremely high angular momentum,
Yeah, those things will be like further away and K will be. The M will be very large, but N will also be very large. So that's not part of it.
At some point, the production will saturate, right? So you will
Yeah.
extract the spin, but
Yeah.
then the final configuration is still kind of time dependent because
Yeah,
it's kind of
It is
stage.
rotating
It's-
around the spinning back.
It's kind of stationary. I don't know. Or static.
no,
It's
like,
not. It's
it's
time
not.
dependent, but still like
It's not. So like I'm going to show you. Okay, so like but like so here let me just say like at when the time like where the superradiance process saturated, we can get up to like 10 to the 78 particles in this cloud. And to answer your question, this lowest superradiating mode is always rotating around the black hole after superradiance has saturated. And during this process, it gives you a time-dependent moment and the mu, which leads to emission of gravitational wave. And so the green things are gravitational waves that are emitted from the system. Okay, so so like that's basically all I want to say about this superradiance effects. So here there are a few numbers that I want to you to like to remember. So there are three length scales in the problem that we'll be studying. So there is the size of the black hole, okay, which is Gm. There is the Compton wavelength of the particle, which is 1 over mu. And remember, like alpha is something that is a little bit smaller than 1. So 1 over mu is always a little bit bigger than the size of the black hole. There's also the cloud size, which is the Ward wavelength of the particle, or like the Ward radius of this rotating atom, which will have a size that is 1 over mu times the exponential constant, and it goes as Gm over r squared. So the important thing to remember is that this cloud is even bigger than 1 over mu, which is equal to 1 over omega, the rotation speed of the black hole when the superradiance. So that's the three length scales, which has this pyramid structure there, because we're going to come back. Then like, there are also three time scales which are important. The first one is the rotational period of the cloud, which is set by the particle mass, and so it's like 2 pi over mu. There is the superradiance rate, which is somewhat slower. It goes as alpha to the 6th power times mu, and so this is the scaling for the fastest superradiance mode. And then there's also the cloud decay rate, and for all of the parameter space that we'll be discussing, the cloud decay rate is set by gravitational wave emission, which goes as alpha 12 power times mu. So, and here again, like the exact number is not very important. The important thing is like the relative size of these three rays. This is the fastest. The superradiance rate is slower, but not so slow, and the cloud decay rate usually takes years.
Okay, justify the power here in the are you going to?
No, like I'm not going to discuss it in detail.
But what's the power? Why we have such a power counting in this?
So like the alpha, well, like it's basically like the decay, like a superradiance rate, and the decay rates are set by the overlap of the cloud with the black hole, and for L and J, L equal to 0, J equal to 1 mode, this thing goes as 2L plus 2J plus 4, I think, which is why there's alpha to the 6. And but it's all atomic physics computation that leads to this power loss.
Oh, so
But it's not very good.
the exponents here are different for different modes.
For different superradiance modes, like yeah, the power is different.
Okay,
And this is the faster one, so it's the one that will actually grow in the variable. Okay,
And do you mean that the cloud will eventually decay exponentially? fast?
power law. Yes.
Or
Yeah, the gravitational wave leads to the cloud decaying with power. Okay, all right. So that's the introduction about the superradiance. Now let's talk about that photon. So that photon is a hypothetical particle, which is like our photon. So it's a U1 field, but like the difference is that it has a mass, u squared, and then like it interacts with us with pins from the ipsilon. Okay. So throughout the talk, we'll be actually using a very specific basis, where the coupling between the star model of charged particles. So JMU star model contain, for example, the electron current, is coupling to the dark photon as a mu prime J mu term, with where the mixing from the epsilon serves as a mini charge of our electron under the star. So you should think of this dark photon field as an electromagnetic field that couples to our electrons with suppressed strands, where the amount of suppression of the strands is parameterized by this. So this is the parameter space of the dark photon. So x-axis you have the dark photon mass mu in EV, and the y-axis you have the epsilon parameter. And here, like I summarized, basically all the experimental limits coming from all kind of different searches for this dark photon field. So the region that we'll be interested in talking about today will be this region here. So throughout all of this region, like in this red box, the processes that will be telling you will happen. But like so on the right hand side, this limit is set around like minus 11 eV. It's set by the size of a solar mass black hole. So anywhere if it is lighter, heavier, then Compton wavelengths like these particles will be smaller than even the smallest of the black holes that we know exist in our universe. On the right, left-hand side, it is set by roughly the biggest black hole that we have in the universe, which is roughly 10⁻⁹ solar masses, where like this limit is roughly 10⁻22 eV. While the upper and the lower bound on the coupling comes from somewhere that we use like a control on our computation, and here like when like the coupling is really tiny, then the processes that will be tiny will happen. So
by the way,
all of this parameter space in this box, something will happen. Yes.
not to nitpick too much, but I think there are a bunch of bounds in that parameter space that you're not showing, like a bunch of heating bounds and things.
Not for the case where it's not documented.
Oh, this is only non-dogmatic.
Yes.
I see.
No.
Well, of course, you're missing our dark ISF.
Yes, this is from last year, December. Your paper is after it. Yeah, sorry.
Can you comment on how to get such small kinetic mixing?
Huh?
Can you comment on how to get such small kinetic mixing?
I think.
And I know this is the right
Comment on that. I don't know. Yes, I won't. But the region like we are actually be talking about today is this region here, because we will be focusing on the black holes that we know are spinning black holes we know that are used in light wavelengths. Okay, so these will be like black holes with masses that are 10 solar mass to 100 solar mass, and which populates this region of parameter space here. I will show you what each of these observable consequences, where do they come from, and hopefully coming through that to this.
Sorry, in the previous plot, typically people show there's a black hole superradiance band that they don't show where limits are. Your work actually drive a limit. that does not extend to very
So
small.
for the, yes, those limits like, do not apply once like the epsilon is bit above like somewhere. Yes,
Okay, so
because like the measurement of the black hole spin is no longer valid. Yes, I can show you more details afterwards.
yeah, by in other words, the typical plot, the version of typical plots with a superradiance band
Yeah.
shouldn't be there in that plot. That's why you need to
yes,
show that.
like, the epsilon is very large, like they should be.
And then how is this particle produced in the early universe? You're just using some freezing or something? How do you produce this particle? Dark photon.
Dark photons is produced through the superradiance instability around black holes, right? They don't need to be dark matter.
So
Don't
you
need
don't
to
need any,
exist.
you don't need any early universe
I don't
production.
need any universe.
So you just need to assume that they exist,
In the Lagrangian, then they are get populated automatically.
and you're not using it to solve any, like the dark matter or anything like.
No, nothing. Yes,
Just need a rotating part.
yeah, I just need a rotating black hole. Everything like I'm telling you, like it happens.
So these things are not necessary for anything, or just like imagining they exist and then like playing.
They are not required to like.
They don't solve any problems.
They don't, yes.
Okay.
Well, you want to it.
Yeah.
You could.
Wouldn't that be a little bit more motivated?
You could, but
Like, what's the
point-
motivation? Let me ask it this way. If they don't solve any problems, what's the motivation?
No, the point is more like, it is not required to exist as any of these components, it could be. Right, but like this particle, like it can, like existing in the Lagrangian, and it can lead to this type of effect.
Yeah, and it has to be a vector particle for
It has to be a vector particle,
It can't be scalar.
it cannot be scalar, like if it is scalar, the same style will tell you won't happen,
I see.
yes.
Also, can you imagine this is a component in the bigger series of some problem? That's that.
It just seems like the space of things that are not well motivated by any particular current issues is very large.
Yes and no. There's a sort of a unique models that can be written in IR. They don't, maybe you kind of be careful, right? So couple through some
Couple a little bit
relevant operators.
Yeah, so,
Okay, I see.
there are two of
Very
these
few
examples.
of these examples you can construct at low energy. So some sense.
Yeah.
But if this particle exists in the Lagrangian, there are no processes in the early universe that could also produce it, like
Actually,
inflation.
a talk that I will give otherwise, but like I'm happy to tell you about that later, but I won't.
You know, I'm just trying to frame
Yeah.
what you're trying to do. Yeah, because if you have this particle in the Lagrangian, it could
Yeah.
also be produced in the early universe as well. That would be
Could.
complementary signals to what you're getting here. Is that
It could, but like, yeah, for this type of masses, like,
for instance, yeah, for these masses,
you probably won't have like a very large, like,
I see.
It very sensitively depends on whether it's Higgs or not. right?
Whether it was, sorry?
Or whether this is Higgs or not, right? So there's like two different pictures.
yeah.
Where there's
So-
loose Higgs, the dark photon?
Yeah. If the mass comes from the Stuckelberg mass, then there is no efficient production mechanism if you just write it by hand. Just because if you erase it, it's decoupling completely. But if it's Higgs, then you have a pair production, basically.
Basically, we can get the Stuckelberg thing from a limit of the Higgs potential.
Right, but
So that's a statement that if you take that
once,
limit, then.
once you are above, say, a typical Higgs mass, right, you have a pair production of these things that don't decouple. But if you is an opposite limit, right?
I see, thank you.
As we,
I see, I caught on, I think I.
Then the subtleties here.
I can, well,
Yeah.
I can pull out my vortex slides, but I think I should. So let me just keep telling you about the dynamics in this. Okay. So yes, so that's all for the introduction. Now I will be telling you what is happening in the superradiance cloud once as it is getting populated. So in this part, I will be explaining to you how, what these four panels or pictures mean. The first one is very simple. It's just a spinning black hole. So let's start from the second one, where the superradiance is populated. So earlier, as I was telling you, so if I have this vector particle, then like I'm going to populate a superradiance cloud around this black hole. And I showed you the A prime vector. From that, of course, I can compute the E prime and the B prime as a result. And remember that these are not photons and they couple to electromagnetic charge particles. And so the charge particles in the cell model see a field strength that is epsilon times E prime or epsilon times. So this is how, so first let me show you how we look at the information space. So on the left hand side, what you are seeing is the electric field. So now like their contribution mostly come from DTA prime, DTA vector. So which are basically the A vector field, which are parallel to each other, rotated by 90 degrees, right? So then like, but like these are not like totally parallel to each other, or like totally straight. And the reason is because there's also this gradient term, which just the. On the other hand, the magnetic field comes from the curl of a vector, and it is basically a curl of current, which is pointing in the A vector direction. So as a result, what you are getting is magnetic field on the current, which are these circles. And as the cloud is rotating around, the electromagnetic field will rotate with it. Okay, so let's see what the strengths are. So the electromagnetic field stresses are written here. So the first thing that is important is that electric field is actually bigger than the magnetic field. So by this alpha factor. And the second is both of them are very large in particle physics units. They can be as much as 10 kV squared. Well, if you're more astrophysicist, then this unit will be more familiar to you, which is 10 to the 10 Gauss. For epsilon parameter of 10.16 and alpha of 20. So this field strength for a lot of parameters space we are interested in are comparable to the magnetic field of a pulsar or magnetar, and that's where like the analogy comes from. Okay, so that's the field strength. The second important thing is the length scale, the size of the object, which, as we said, is GM over alpha squared. So for 1 solar mass black hole, if this is 100 kilometers, if it is 10 solar mass black hole, then it can go up to like 10,000 kilometers. So what you're seeing here is a really large volume of very strong magnetic field, and the volume is way bigger than the volume of a pulsar. So a normal pulsar around the case. So the energy scale in the problem, which are of interest to people who are more familiar with particle physics units, that is basically the electric field strength times the cloud size. And this for the chosen parameters can go up to 10 to the 10 GeV. Okay? So which means, and this is probably the most energetic like particle accelerator somewhere in the universe.
Sorry, so what happens if we take epsilon to be larger than 10⁻⁶? So you will have a string effect, and then
you will always have finishing rate.
yeah, and then that will discharge the A prime, and then
I will show you.
okay, right.
Okay, right. As Junwu already said, there will be production and dancing lists. Okay, so that's basically the next picture. So there are many processes that leads to pair production. So the most important one is the combination of synchronous radiation and assisted numerical production. So what happens is this charged particle, even if you just have one charged electron, which exists in the universe and went into the superradiance cloud, it will get accelerated, and it will encounter fields which are rotating. So like it will be like somewhere like a perpendicular to its like a directional motion. It will emit synchronous radiation, and this radiation will then like interact with the electromagnetic field and pair produce. Okay, so this process is called assisted production. It's much more efficient than the normal production, and the rates are summarized very nicely in this paper by Max Morning. I think there's a student here, and also the great Michel Roche. So with these processes, what you can do is take the one charged particle, send it into the cloud. It will lead to a photon being emitted, lead to more pair production of the charged particles, So you can start with 1, go to 3, go to 9, go to infinity, right? And all of this process is exponentially growing process. So it quickly populates the cloud with a lot of charged particles. Okay, so here are 2 plots which shows you how fast this process happens, and like in 2 different cases. So here the curve shows the boundary where the curve production rate is faster than the time it takes for this electron to exit the superradiance cloud, which has the size of the mu. So anywhere above the blue line for a 10 solar mass black hole, or like the orange line for a 100 solar mass black hole, these charged particles will efficiently produce and quickly populate this cloud with a lot of charged particles. And this is where like this limit of 10 minus 11 come from that I was showing you earlier. Right. So on the right hand side, what we have is the production, the plasma production rate or the time over the superradiance rate or the superradiance time. So here, like we basically have like the plasma production rate over the superradiance rate, which is equal to 100, 10 to the 4, 10 to the 6 times the 8. Okay, so the exact number again doesn't matter. What you are seeing here is that for all the region where the pair production can happen, it really happens much, much faster than the superradiance rate. What it means is that as long as the superradiance cloud is growing to some threshold where pair production events can happen, this plasma production grows very fast and leads the system to some sort of equilibrium, and then the superradiance cloud will continue to grow while the charged particle density will grow adiabatically with this growing superradiance cloud.
Is the
So-
superradiance cloud still growing exponentially?
Yes, afterwards.
Okay,
Yes.
because in like the scalar case, when you have self interactions, doesn't that kill the exponential
Yeah,
growth?
so like in the case of the dark photon, right? If you have like this charged plasma, it only gaps one of the 2 degrees of freedom. It gaps the photon, while the dark photon will remain like at the mass mu, independent of how much like the mass of the.
Okay.
And that's the reason why there's minimal back reaction on the growth of the vector. Okay, so yes, let me stress here. The point is that this transient process is happening really, really fast in the beginning of the growth of the cloud, where the cloud still has a very little amount of particles. And after that, it is somewhat adiabatic. So you shouldn't be able to find any observer signature when you tag this transient. All right, so but we still want to understand the transient, and in particular, we want to understand like what type of stability or metastability states that it leads to. And the question we need to answer is not only how does the cascade start, but how does it end, right? And to understand this, let's draw an analogy with something that we understand, which is a thunderstorm. Okay. The thunderstorm starts when you have an electric field, which is or like a potential difference between the ground of the Earth and the cloud. Right? So when such an electric field is established and growing, at some point, like there's a breakdown, and the charged particles start to flow through the lightning spark, which is basically a current that brings positive charged particles to the top. Of course, these are not really positrons, and the negative charged particles on the ground, right? And these charged particles, which get separated, creates their own electric field, this purple electric field here, which try to counterbalance the blue electric field you saw set up this. And the cascade stops when I have E equal to minus the blue E, right? There's no electric field, no force anymore, and the cascade comes to an end. Of course, this is a very stupid way of explaining this, because no matter whether it's a blue electric field or purple electric field, it's all electric field. It's all set up by charged particles, real charged particles in the case of the lightning strike. In the case of the superradiance cloud, it's quite different, right? Because the electric field, the blue electric field, which is set out of this initial accelerating field is actually the dark photon, which mixes with us through this kinematic signature. And while the charged particles that get separated are real standard model charged particles, which establish the purple electric field from these real charged particles. And again, like in the previous case, the balance is reached when they sum up to 0. And now as the vector cloud will rotate, of course, these charged particles will rotate, and it is basically a rotating dipole moment going from like, the one side of the charge. Yeah. Right? So what you have here is you establish a dipole which is rotating around the spin direction of the dipole. So the spinning cloud itself is trapped gravitationally, but this electric dipole is able to radiate to standard model photons. Okay, so let's remove this radiance cloud, and now what we are left with is an electric dipole moment, which is rotating around the spinning direction of the black hole, and that is very similar to something that you know, which are pulsars, right? And there are some artistic view of the pulsar, but if you are like serious like me, then a pulsar is basically a magnetic dipole moment which is rotating around the spin direction of the nucleus. Right? So here, the object we have is an electric dipole which is rotating around the spin direction of the black hole, and which tells us that they probably have a similar radiation. And that's when we thought we are done until we encountered this problem here. As I told you, I'm going to come back to this plot, and now I'm coming back. So on the left-hand side, we have a little pulsar, which where this is the size of the neutron star, and 1 over omega, the rotation frequency, is the size of the lattice cylinder. And in the case of the neutron star, of course, omega times r is smaller than 1 because the surface of the neutron star can not rotate that fast. And as a result, the lattice cylinder is bigger than the size of the neutron star, whereas the magnetic dipole moment is. Right? In our case, it's the opposite, because the size of the cloud is actually bigger than 1 over mu, which is equal to 1 over omega, when the superradiance condition saturates. So the electric dipole is actually bigger than the lattice cylinder. And now we know, like the picture that I was telling you is actually not the case, because of course, like the charged particles here cannot really rotate fast enough to keep track with the oscillating dark photon. So basically, this comes to the fact that omega times r cloud is 1 over alpha, which is a number that is always bigger. So now we'll do it. Well, the analytical method comes to an end. Now I'm going to show you simulations. So what I'm going to show you now is a simulation of how does the electromagnetodynamics work inside the superradiance cloud. Okay, so just to bring everybody to the same page, let me start with pulsar simulation 101. Okay, so when I'm simulating a pulsar, what I'm doing is I'm solving the Maxwell equation, of course, around the neutron star in the magnetosphere. Right. So of course, like if I just have this equation, I cannot really solve it because I have this J mu, which I don't know what it is. So what I need to do is I need to introduce a prescription which relates the current in the system with the background electromagnetic field. Right? And that thing is generally called Ohm's law. For example, in the case of the conductor, the Ohm's law is J equal to sigma E, where it relates the current or the charge flow with the electric field, which is acting on the conductor. So this is the force that is pushing the charged particles, and this is the resulting current, and that is the relation which is Ohm's. So here we need to introduce an Ohm's law as well, and of course, like the system contains both electromagnetic field. So the force that is actually pushing on the charged particles is the Lorentz force. So what you are writing down as Ohm's law is a relation between the current and the Lorentz force in this combination. With this, you can plug in the equation and you can solve it. You can solve for E and B. outside the neutron star. In particular, you can solve it in the limit where sigma goes to infinity, which is otherwise known as the force-free limit, because if this is infinity, then this has to be zero, where the Lorentz force is equal to zero exact. Okay, so we want to do the same. So now what do? We need to solve two Maxwell equations. We need to solve both the Maxwell equation for the photon and also for the we need to have a prescription, which is the Ohm's law. Now, not only the standard model of electromagnetic field is pushing the charged particles, also the left one. So now the Ohm's law contains all of these components. The real almost currents that we introduce is much more complicated than that to make the simulation actually work. But idealistically, or like this is the best we call it. So now we can use the background that photon field and solve for the electromagnetic field as we go. Originally, we are also trying to solve it in the sigma going to infinity limit, and then we quickly realize this is impossible because the system that we have wants to always be electric field dominant. As I was telling you earlier, the cloud wants to produce a system which is mostly electric field, and due to this insufficiency of this the shielding mechanism, it is very hard to maintain a magnetic dominated region everywhere. And as a result, instead of doing it in the sigma to infinity limit, where we force the force always to be zero, we are actually doing the simulation with average in sigma, making sigma bigger and bigger until at some point we reach some sort of static solution or like a semi-equilibrium solution where we can extract the luminescent forms. And I'm going to show you more details. Okay. All right. So now let's do the simulation. We are seeing this dipole rotate, right? As I was telling you earlier. So now let's see what the simulation actually tells us. So this is the result of the simulation, where the blue and the red are basically positive and negative, and the darker the color, the larger the charge density. So what you are seeing here is the field like some dipolar form, where there's a charge separation between the two parts inside the cloud. But the other thing that you see very clearly is that there is a significant lag the further away you are from the cloud cell. And this lag is basically coming from the fact that the charged particles outside cannot really keep up with the rotation of the cloud. Okay. So with this simulation, we can compute a bunch of things. For example, we can compute the charged particle density. We can compute the electromagnetic field in the system. And we can compute, of course, the dark electromagnetic field and the cloud density. So the important thing here is a prospect that shows that the charged particle energy density is way smaller than the electric field and magnetic field density, which are, again, much, much smaller than the dark electromagnetic field density or the cloud density. And this is important. So the first inequality is important such that the resistive force-free magnetosphere prescription is valid. Well, the second inequality is important because we do not want to account for the back reaction on the dark photon.
Can I ask why do you do such a simulation? You want to get the correct time scale of how the angular momentum of black hole got extracted away by such.
We want to understand, when we have this rotating cloud,
yeah,
what is the speed it leaks energy into the standard model charge path,
okay,
and which gets emitted from the system.
But the black hole angular momentum is already extracted
into the cloud.
Yeah, into cloud. And cloud can emit release energy in a slower rate. But
what is that rate is what we want to understand.
Because
that's the observer.
That's the
we want to understand how much power is released from the cloud into the plasma, which then get released into the side, right? And then we want to understand, as a function of time, how much energy is actually being seen tend to infinity, which we can see. And this energy will be electromagnetic energy that are propagating to us. And as I'll show you later, these energies will mostly be X-rays.
But how can you distinguish that from regular standard model process?
We'll show you. Yes. Oh, that question, I will show you.
Let me say, I extract the black hole spin via the black hole merger, right? So, which has nothing to do with the
The black hole merger gives you the spin of the.
yeah, tells me that's observable. I can have a statistical statement on the the spin of black holes. That has nothing to do with this cloud, right? In some sense, I can store angular momentum into the cloud and let it decay. Radiant energy angular momentum slower, but it wouldn't change my observable, which are the
No, the observable is the X-ray.
not the gravity wave of black hole merger
And
system.
I will show you, like the observable, real observable that we are tagging is X-ray. Yes, I'll come over. Yes, and I will show you, like, I will answer your question for me like that, I promise. But we are not at the phenomenology yet.
Okay, a second question is, suppose you have two black holes, each with its own cloud, and black holes themselves are not spinning, but the clouds are spinning, and these two black holes are merging, then what happens?
Yeah, so I would assume the merging system is dominated by the black hole merging system, which I don't care about how much angular momentum is contained in the cloud.
No, like the system that we want to tag are the final state of a black hole after a black hole merger. And we want to do a follow-up electromagnetic study after the merger has happened, producing the spinning black hole and asking like, what is this spinning black hole doing?
Okay, okay, I see. That your observable is after burning, let's call that.
Right. Yeah. Okay.
So possibly a stupid question, but how about the emission of A prime? Is that relevant?
Like those are like bound. Right? It is massive field, so it's bound.
Oh,
But the superradiance cloud still extracted all of the angular momentum you would have expected, even if you didn't do any of this plasma stuff.
No. It will always extract the like angular momentum from the black hole.
Yeah.
That part is independent of like whether it has charge current interactions with the sun or not.
Yeah.
The question is like, what is the observable consequence which will require this?
Well, so I mean, maybe you'll get to this, but then what cuts off the black hole superradiance bounds? Like you said, the black hole superradiance bounds shouldn't go above.
So like so those then I need to really tell you like where the bonds come from, like a measurement of black hole spin, right? Assuming like you can measure the spin through like the disk dynamics. And the disk dynamics, like the equation disk dynamics, which gives you knowledge about the black hole spin, is totally like altered by the presence of this cloud.
Oh, okay.
So like these measurements, like, yeah, you need to really think about like where do this measurement come from? Yes, that's what. Yeah. Okay. All right, so then like let me show you this picture again, video again. So like what you're seeing like is this rotating dipole, but also like these small scale structures, right? So you might think it's a numerical artifact, but they're not. They're actual physics, and that was the important things. So another place you are seeing the same feature is the magnetic field strength. And here, like what I'm showing you, is the magnetic field strength, or V square, as a function of sigma and the location along the ground. So sigma over mu equal to 0 means like there's no plasma, no conductivity, and this is basically the background solution, which is just the superradiance cloud. As you are increasing the conductivity, what you are seeing is this small structure emerging from this outside, which eventually sigma over mu equal to 20 take over a whole of space. So these pictures, of course, has similar structures as the video I'm showing you, which has these filament structures. So the question is what they are they? Right? So what is happening here? So what is happening here is turbulence. Okay. So I'm Canadian, so I get to show you this video, this plot. So this is Niagara Falls. I'm in Canada.
Your passport has changed already.
Yes, I'm in Canada. I'm not Canadian. Well, like research. So on the top, what you have is a laminar flow, while on the bottom, what you have is a turbulent flow, right? So which flow it is determined by the Reynolds number, which depends on the velocity of the flow, the velocity, the scale of this flow region, which is the size here, and then the viscosity from the unit, right? So if your the velocity is bigger, the size is bigger, the viscosity is smaller, then the Reynolds number is bigger and it is more turbulent. So here, what you are seeing is something similar. So the efficient motion of the magnetic field inside the superradiant cloud is actually very analogous to the Navier-Stokes equation. And you can define a parameter called the magnetic Reynolds number, which defines the speed of magnetic field reconnection or like a magnetic turbulence. So here, the magnetic Reynolds number depends on also three parameters: the velocity of the flow, which is basically the rotation velocity of this cloud of charged particles, the extent of the flow, which is basically the size of your superradiance cloud, or how far you are from the center, and this conductivity parameter, which parameterizes how likely it is for a magnetic field lines to be. So this is what basically what you are seeing here. It's the magnetic Reynolds number at work. As you make like this conductivity bigger and bigger, it is more likely to be turbulent. The Reynolds number becomes bigger. The Reynolds number first become big, far away from the black hole, because that's where like these two numbers are bigger. And then like as my sigma continually increase, at some point, the turbulent region or magnetic field reconnection is happening everywhere in the system. Why do I tell you about this? Right? Why do I tell you about this? Because this is also seen in a certain location. And in this video, what I'm showing you is the energy dissipation rate as a function of location and time. So hopefully this runs. Oh yes, this runs. Okay, so what you're seeing like the red color is where the energy dissipation from the superradiance cloud into the charged plasma is dominated, right? And you are seeing the same filament structure emerging, right? Which motivates us to close in into the region where like the energy is released, zoom in, zoom in, zoom in, to these points where the energy release is maximized. So here, what you're seeing in this figure is the red region where the energy release from this effect is maximized, right? While the lines, the white and the orange lines, shows the region where the magnetic field strength is strong. So what you are seeing here are magnetic field lines which are reconnecting at this location, which is also the location where like the energy is released. And this is how you see that these two processes are actually, well, like the magnetic field line reconnection events are what leads to the charged particle like acceleration, energy dissipation, and energy release from the system. Okay. So with all this understanding, we can compute the energy release from the system. So there's this complicated units, but the important thing is as I'm increasing the sigma, it eventually like separates to a value that we predict. So the luminosity we are seeing can be at as large as 10 to the 43 per second for epsilon of 10 minus 7. And this is a luminosity that is 10 order of magnitude brighter than this. Okay. And this is basically the similar information, but in the plots that I was showing before, these lines shows you the luminosity, like constant luminosity contours for tensor mass of the solar mass.
Sorry, I forgot the meaning of the parameter sigma.
The conductivity. So physically, the conductivity can be very, very large. But of course, I cannot simulate that. So the thing that we are doing is making the sigma large and see like the system saturate. And that's also observed in the pulsars, which motivate us to do these studies. All right. So that's the emission power. Then like we also like observe like the many processes, which is its periodicity, and the period is 2 pi over mu, as I promised you earlier, and it's independent of R. So it's independent of the black hole. So then like the other information we can extract from these simulations is the average magnetic field strength in the cloud, which is the quantity that is most important to understand like what is the emission spectrum. So we expect there to be a synchrotron peak around KEV and inverse Compton peak around G. So the relative height of these two peaks is largely unknown, which is why we need to do like searches both in X-rays and okay, so that's a summary of like all the dynamics. In the interest time, we'll just quickly switch to how different knowledge. So next, I will be telling you how to search for this object. And the way to search for it is using analogies with pulsars and magnetars. So I'll be telling you about two structure strategies. The first one starts with a gravitational wave that comes out of black hole merger. And we try to tag these spinning black holes that are known to exist in LIGO and see if they are emitting electromagnetic radiation. The second type of search, like we start with the pulsating objects, which are emitting electromagnetic radiation, and we will try to see whether we can see the gravitational wave coming from it as well. So I will give you more details on each one of them. So the first thing is a LIGO follow-up. So here, what we are using is basically this plot I'm showing you here, where you see the luminosity of the electromagnetic energy first grows exponentially fast with a time scale that is basically the superradiance time scale, which can be hours to years. So here, like we have like an R of 0.1, and the same basically goes within days. Right? And then like it will have like a long power law decay, which are set by the emission of gravitational. Okay, and this can last for like years. So for each of the black holes that are observed by LIGO, you will have a different alpha parameter, and you are going to have a different like a light curve given the same black hole mass. Right? So this should be a parameter that is universal to all the black holes that are merging, well, not merging LIGO, but like it's seen to merging LIGO. And the LIGO give me this parameter. So in principle, given like a dark photon mass, I would be able to predict exactly how these light curves look like.
Are these things going to be emitting like pulsars in that they have like one like strongly beam direction and you really only see it when that's facing at you?
So like the X-ray pulsars, like usually the opening angle is very large. So the answer is like most likely not. So you're going to see like a pretty much 4 pi emissions in X-rays.
Okay, for these guys, it is pretty much isotropic.
Yeah.
Yeah. Essentially turbulence emitting.
Yeah.
Yeah. So that's
so but like the luminosity is still changing as a function of location and time, which is why like we still possibly see some like a periodicity. For that, like we need to do like more big simulation to know. But like the search that we're proposing doesn't really rely on that. So if it is pulsating or if it is not pulsating, like we can do the same thing. Okay.
Sorry, just to interrupt. The meaning of decay means I have such a cloud of very complex system. They're just slowly drifting away due to the propagation.
No, like
what's the meaning of
they
decay?
are losing mass through the gravitational wave emission. And as a result, like the signal will slowly go down, right? Because at some point the cloud is not there. Okay, so these light curves can be used to search for these events, right? Like we are tagging regions where like a black hole has emerged, and we can predict when like the signal will rise and when the signal will decay away. And we know exactly the shape of this decay away, which allows us to use the different telescope to look for these events. So in this plot, we are showing you basically what we can do with the existing known like black holes. Of course, we didn't do this analysis yet. Those are like data in the Fermi, which we are not analyzing. But in principle, like, we need to rely on like LIGO black hole mergers that will come in the future. And of course, we're going to see them. So in the future, with better localization. And these are the analysis that we are actually thinking of doing. So the X-ray line is the sensitivity if we can have access to E or zeta data, which unfortunately we cannot. And then the radio line is using time as a detector to tag the radio emissions from these objects. So we are now working doing a Fermi analysis where we stack a bunch of Fermi events and actually like the events that we already see, and the important the usefulness of the Fermi comes from the fact that Fermi is seen in the sky every time, like all the time, like every 3 hours. So like with existing data on tape, we can already do analysis, which gives us very interesting for regions we can probe, the space region. Okay, and as I said earlier, like the search is possible because all of these events coming from different black holes is totally determined by one single parameter, which is the dark matter mass, and we can cross correlate different events to get a better sensitivity and region mass. So the second type of search is to tag like the existing pulsars and asking if they are actually black holes instead of neutron stars. Okay. So there are two defining features of the pulsating source that we are interested in. The first one is that the F dot is always positive because the cloud is always losing mass, and the gravitational binding energy is becoming smaller. So that's one thing. F dot is always bigger than 0 compared to normal pulsars where F dot is always smaller than 0. The other thing is that all of the pulsars we are interested in has pulsating period, which is set by the dark photon mass, which is the same across all different pulsars. So we should expect all the fake pulsars to have exactly the same period. So these are basically the two ways that we use to select the pulsars that we are interested in. And from a catalog of 3,000 pulsars, and then we try to look for the gravitational wave that is coming from these pulsating light sources. So the reason why we can do that is if we fix F dot and F, the object we have has a much bigger particle moment, and as a result, it is producing much more gravitational wave compared to a normal pulsar, which is neutron star. So the red dots are the gravitational wave amplitude for like a black hole pulsar, given the F dot and F, and the stars are the corresponding amplitude for neutron stars. So, and the line marks roughly the sensitivity of the light bulb, the one light bulb. Okay, so so then like we did this selection, we select like order 30-40 of these pulsars, and we found like tens of doublets, meaning like 10 of these objects, which has frequencies that are within 10⁻³ of each other, pairs, and then like a triplet, where like 3 of the pulsars all have the same frequency. So
totally different locations. Totally different locations.
Totally different locations, but same period. Okay, and the triplet is somewhat like, but like we kind of know like the triplets, like at least one of them is definitely a neutron star. So we're not totally very excited, but like it's possible that some of these are actually black. And in this plot, what I'm showing you are basically all of these neutron stars that can, well, all of these pulsars, which can be both neutron stars or like black holes. So the gray shaded region is the region that is already excluded by like a stochastic gravitational wave search. Okay. So if it is above this band, then like these black holes will have been emitting too much that is already excluded by data. So this line marks the location where if you do a dedicated continuous wave search, you can find these objects in gravitational wave. Right? So you can see like there is a hand, well, like a dozen of like these objects, which can potentially go off if we do a dedicated search pointing at these processing of this. And that's very exciting. And hopefully, like we can understand. So that's all I want to say. So now let's come back to this figure. And as I promised, only I talk about phenomenology. So in this purple band, well, above this purple band is the region where we think like in the next round of LIGO, like we will find like this object we can tag and look for its electromagnetic follow-up in the shape that we are interested in. While this green region are the region of parameter space we can find some of these anomalous pulsar, which can potentially be originating from black holes. So that's it. I hope I convince you, like with spinning black holes, dark photon superradiance, we can produce a cloud of dark matter, dark photon, which through this assisted Schrödinger production processes populates a cloud of charged particles inside this superradiance cloud, which through its own dynamics leads to turbulence and the turbulent energy emissions that can be looked for with various frequencies. And that's all I want to say. Thank you.
Thank you, Crudely, for an excellent talk. Any questions?
So what is the experimental uncertainty of the pulsars in the frequency, and what is your the experimental uncertainty of the period of the pulsar?
Oh, the period experimental uncertainty on the period of the pulsar is almost zero. It's like this 10-ish or smaller.
And if some of them are caused by the dark photon, then we will expect them to have exactly the same frequency,
Yes.
even up to the experimental uncertainty.
No, up to like the velocity.
Up to which
So like we
ones?
do not know like which way they are moving. Like they're all in our galaxy.
Yeah.
Like they can be moving away from us or like close towards us.
Oh.
So there's this like Doppler redshift, which can be like 10⁻�3, right? So the way that we select are like we are tagging like two frequencies which are within 10⁻3 from each other.
I see. So in principle, if we know their velocities, then we would be able to match it almost precisely.
Yes, but like that measurement will be really, really hard.
If you do either of these searches and don't see anything, can you get any robust exclusions and parameter space out of that, or?
Honestly, like I don't really care about exclusion limits. But because I mean like we are searching for something new and I care about reach. But if like you are doing these searches as electromagnetic follow-up of like LIGO black hole mergers and you are not seeing like any of these emissions in like any of like these bands, then you exclude the parameter space. So we need to like look both in X-ray, gamma ray, and radio, and we don't see it anywhere. Then like we know like it's not emitting electromagnetism, and as a result, that region is clear. So the purple line above the purple line, we can have exclusions. The green band, like it will be statistical. You can say like, oh, like I expect this much likely in the galaxy, and we don't see it, so there's exclusion. But those are like much less reliable. For the LIGO follow-up, I think it is very reliable if you can search like in multiple bands, and you are not seeing it.
Okay, like you have some statistics on like enough black holes merged to give a highly spinning.
All of the black hole mergers give you a, well, not all, like I think all but one gives you a black hole which has a spin of 10.7.
Okay, and that's enough that it.
That's, yeah, that's way in.
So basically, you're saying that if you don't see anything in that region, you can't extend parameter space to see. You can't enlarge the parameter space to see this effect. Is that what you're saying?
If you are not seeing it's like any like X-ray, gamma ray, like or radio, like from like let's say like the next 20 like black holes that we see, then like we exclude this parameter space.
But then can you change parameters to have another region to look at, or,
I mean, like you can go to lower and lower.
yeah, so you can just keep lowering,
You can keep looking, yes, but like.
But is there a
the-
minimum value that at that point I can't use this technique anymore?
Oh, that will be 10 minus 11,
I see.
when like the paraplasma production no longer happens.
Oh, okay, so there is kind of
There is a-
eventually a lower
Yes.
bound, yeah, I see.
Yeah, so, right, so as you see here, like all the things I'm telling you here, it's around the isolated black hole. And the reason, well, the LIGO is very important for that, because like we know these black holes are isolated, that are produced. In the case where like they are not isolated, it's actually much more complicated, and that's the thing that we're working on. Yes. Yeah.
In one slide, you said that the energy scale is around 10 to 10 GeV. What does it mean?
Oh, the 10 to the 10 GeV is just to show you like how big, like give you a sense of how big the electromagnetic field is, and how big is the extent of the object is. Like no particle is actually getting to that energy, because like the charged particles will like be accelerated a little bit, and then like will just keep emitting, right? It's like a secret like you cannot really like accelerate the electron energy to infinity. Right? It's continuously emitting. Here is the same. It gives you a sense of like the energy scale that is possible in the system, but in reality, it's not something that is to observe.
Or even if I have a cosmic ray that happen to enter this cloud with strong electric field,
No, like you are not seeing a cosmic ray from that type of distance.
I'm just mean in principle, do I get I should
Well,
be
you
able
can,
to,
like some of the electrons might escape,
yeah.
but like that rate is too small to do that.
Can you apply this to the like massive cloud?
Yes, yes, you can, and that's the same thing I was telling you guys. Like, so LIGO is very important because we know these things are isolated, right? Supermassive black holes, they usually come with a disk. So now, like so the project that we are doing now is to understand like how does the cloud interact with the disk. And I was just here like in a talk by Joe, like Darling, who was talking about like flares in solar system, and which are basically like the same type of dynamics we are seeing like in the accretion disk case, which is very cool. Yeah.
So returning to this topic of relative orientation of the rotation of the cloud and the rotation of the black hole, right? I could have in principle an angle between the two, right? And the energy will depend on
An angle between what?
your cloud has a rotation and your black hole has a rotation.
Yes.
So in principle, I could have a configuration that would have this two angular momentum not.
You mean like the rotation axis can be different?
That's right. Would like to know how the energy depends on the rotation axis. You know, like
No.
I ask, there is like in a hydrogen atom, there is a hyperfine structure, and there are like two-level system, but that's because the angular momentum is quantized, right? So here it's not quantized. And so
No, for a single dark photon particle, it is still quantized.
no, but I still can think of it's still a large angular momentum of the whole cloud, right?
Yeah.
And it's still macroscopic, right? And it's still a large angular momentum of the black hole. So nothing prevents me from having a relative angle between, even a small angle between the two. And that should store some energy. And that should lead to some, instead of a two-level system, it should lead to some band structure and so on. I do not know if in any of these processes, this angle would start wobbling at all, because the energy associated with that angle would likely be small. but I'm just curious how.
No, I think like the each dark photon, like their energy still has to be, like their like spin direction still has to be like in the d direction, such that m equal to
What precision? This is an angular momentum. I could choose I don't know, a slightly different axis, slightly. I mean, like the absolute precision. There is no other direction.
I think like the fact that like there is so much like of this dark photon like in the same state actually makes it hard, like more rigid, like you cannot move it.
Then the energy, you're telling me that the energy is infinite in that angle.
No, like I'm just saying like
Is this at all feasible to think about the dark matter having angular momentum in one direction and the black hole having it slightly in a different direction? Then there is an angle between these two angular momenta. I understand that the energy will depend on some end by the scalar product of that. So there would be a cosine of that angle somewhere, right? So there would be some band structure, at least theoretically. You're telling me that you will never see it in the
I think
in the superradiance process, because you will always be emitting into like the bottom of that band or something.
so like I think like in the superradiance process, like you're always populating the same mode. Like if you invoke like a perturber, then that perturber can like lead to precession. And then like you are going to get like this thing, which I think Daniel Ballman and his collaborator was talking about, right? Like where like you can have this type of level mixing. So the system that we are interested in, like those perturbations are all axisymmetric. And I don't think like these perturbations are going to like lead to us like
that's a different story whether this perturbation is realized or not, right?
Yeah.
But in principle, again, think of this angular momentum not being totally aligned, right? I just want to know the spectrum of the system. Like there is the total angular momentum 0 and 1 for the hydrogen atom, but that's because of the quantization. Here I could have slightly off directed, right?
Right. So like you can talk about that. Like then like I would say like if you have like let's say like a cloud direction which is processing around like the spin direction of the black hole, you can decompose that into like a combination of like this hydrogen wave functions, right? And then like each one of them.
It's
like,
a classical system at the end of the day, right? Because the momentum stored, angular momentum stored is infinite, right? Is super large, right? So therefore, I'm just asking if I start, let's say I start from the initial condition that has some cloud and the black hole angle between the angular momentum, right?
Yeah.
So then there will be some dependence of energy on that, the cosine of that angle.
So I think superradiance won't like only like a.
Yeah, I hear you that you're saying that it will always populate the angle equals to 0, but that doesn't answer my question as to how the energy depends on this angle.
I think like the way that you compute it is like a find that state, decompose it to like a bunch of modes, which all have different energy, and then like sum it up. And I think like that will allow you to compute like this energy difference.
But just from the general principle, you got to be a cosine of that
angle. I think mostly yes, yeah. So now, right? Yeah, so possible, but it's hard to get.
Then the next question is when you have this rotating cloud and you have the various instabilities popping up here and there.
Yeah.
It's still much smaller in energy than the total energy of the
waves,
right? So it will not, but then it depends also on the stiffness of that angle, whether this can lead to a coherent.
Yeah, if you are changing that angle, you need some perturbation which is not axisymmetric, which is not something that we can generate.
but you showed the pictures that with a different place and time, different.
Yeah, like the each of single one of them is very tiny, right? Like when you sum over, like it's just like average to like a axisymmetric condition.
If your energy depends very shallowly on this angle, then there will be a diffusion of that angle. If you even have a non-regular perturbation,
Yeah,
you
you can
will average to zero, but you will excite that angle.
I hear you. Like you can have like this thing like what's it called? Like Brownian motion type effects.
That's correct.
But like I think like the cloud is just too rigid. Like the cloud has like a mass of like a solar mass. Like it's very hard to perturb it like in any way.
Then it's a question of what energy it comes back, right? If the energy of this relative motion is small,
I hear you.
then you can still store your energy in that relative motion.
Right.
I do not know.
Thinking about the numerics, I think it will be like order epsilon squared or like yeah.
But I thought that kind of effect is kind
Epsilon
of,
would not enter.
No, but like the charged particle will only be order epsilon squared.
Yeah.
so, but am I correct that kind of effect is kind of included if you solve the equation portion, no? Of the
Yes,
boson,
yes.
because, you know,
In principle, like it's good.
I don't know the vector boson case, but you know, scalar case actually. So you just solve the Klein-Gordon equation,
Yeah,
right?
yeah, exactly.
And that involves the effect of the spin of the black hole.
Yeah.
So from that, I think you will couple the spin of the black hole to like, your angular momentum of the mode that you constrain, like a scalar mode. I think the effect is that, for instance, like a hydrogen atom case, we can just expand this mode by the spherical harmonics. But instead, because of the presence of the spin, I think you have to decompose it by a so-called like spheroidal harmonics or something. That involves, yeah. So scalar case scalar and the vector case vector, right? And that I think is kind of including this effect of the interaction between angular momentum of the particle and angular momentum of the car.
Yeah.
I'm just asking a very simple question. Does this give a band structure?
Yeah, I think so. And because of that, like, you know, for instance, like, you know, spectral harmonic case, like, you know, the eigenvalue is like L+1, right? And that is going to be modified, and that will enter your like an eigenvalue of the energy. So I think that fix.
Right. But yes, the thing that I was saying is like that is already like in the computation of like the mode. So like whether it's spin up and spin down, like the mode will be very different. So in the case of the vector.
On a literary angle.
Yeah.
Can I ask you a question? How well are these angles aligned? Are they aligned to H bar kind of angular momentum or not? Right? Again, because I can ask these questions and don't have an answer.
Yeah, I think it's I think it's very small.
Are these angular momenta aligned up to the precision of H bar or not?
Up to H bar, I don't think so.
H bar is the measure of the angle.
Yeah, that, yes, right. But like, yes, I would say like it's I think it's at least aligned to the level of epsilon squared. In the case of
because of the instabilities are proportional.
Yeah.
Let's have epsilon equals to 0.
Huh?
Let's have epsilon equals to 0.
Yeah.
Then are these two angular momenta aligned to accuracy of H bar?
I think without a perturbation, I think like order H bar.
H bar.
Yeah.
So because this is the best sort of quantum system ever existed, right? Because you store 10 to the 57 particles, and they're like coherence with the angular momentum of the black hole is H bar. So that's I mean, maybe, right? But I'm just
yeah, because like I think if I think about the numerical simulations, of course, like they are not like 10 to the 70 particles, right? Like, but like they are 10 to the can be like 10 to the 5, 10 to the 6 particles. In those simulations, I think all of them are aligned like exactly in the same state in the simulations.
Fine. If I have a combination of the black holes with different angular momentum, each of these black holes will have the cloud aligned with the angular momentum of h bar, right? To the black hole angular momentum. I would say no, like my gut feeling tells me no, but so there would be some growth, right? With slightly off, and not that will depend on how this exact thing grows, right? But maybe you're right, but. Somebody should investigate that, because this would be like the most perfect quantum system ever, right?
Yeah.
With 10 to the 60 particles and absolute alignment.
I hear you. I think that's what Will is seeing in his relations. But yeah, we can check and we can come back to you. We never like ask like if all of them are the same. Like, but I think like all of this.
Yeah, so we have extended discussion, and we're lucky we'll have Curry for another 2 days. So I think we can continue the discussion. He's up to 75. Let's thank Curry again for the very nice talk.
Sure, also wanted to ask one question. So, like going back to this big picture, like people usually say, like you might also have some dark particles that are charged under this dark particles.
You're right. So our speaker wants to for your interest. Let me know.
Then you can also produce these dark particles, right? Like a dark EV.
Yeah. In that case, like once that particle is produced, like the cloud is.
Okay. So then the story is completely different.
But I did,
The cloud, the particle is produced, the total cloud.
What is this?
Well, like, of course, like you can have demands now. Right? In that case, like the company is so tiny, it doesn't give a shit.
Okay.
But
So other constraints.
once you have once you can start the showering process, then the cloud will be destroyed right away.
Is it because of other constraints?
Yeah.
Yes, as well.
Yeah.
So this is probably a stupid question, but can you get non-linear effects of the self-interaction of the dark photon?
That was unreasonable.
Yeah, it's fine. Like I will give it to him. No, like there's no self-interaction. There's a different.
Non-linear.
That's what
Electron loops.
you don't get
Yeah, I just probably.
I
thought-
can't.